Okay, let's get started. So we are getting into switching concepts. So should be a little bit of review overall, and then in the next video, I'll start getting into a little bit more information as well. So starting off, kind of a couple of things that we're going to be talking a little bit about is getting into, again, how a switch actually forwards traffic. Again, this hopefully is a bit of a review, but it never hurts to kind of go through it. So the primary thing to look at is a switch forwards traffic based off of MAC addresses. So switches operate again at layer 2, the data link layer of the OSI model. So we have two primary aspects of how it kind of establishes and grabs information through the ingress and egress ports. Ingress just means traffic that's going into this switch, and egress just means traffic that's leaving the switch out a specific interface. So when we're looking at our traffic and how information is kind of being passed back and forth, we want to kind of take a look at the MAC address table, or also known as the CAM table. So traffic is stored in the switch, and then the switch makes forwarding decisions based off the ingress interface and looks at the destination MAC address. So what that means again is it takes the traffic, looks at the traffic that's going into an interface such as FA01 here, looks at the destination MAC address in that frame header, the layer 2 header, compares the destination MAC address to its known CAM table, so what areas it knows, and then makes its forwarding decision based off of what matches and sends it out the egress. So for instance, what we have right here is I just have a little network called 192.168.10.0/24. I've assigned .10, .20, and .30 to those interfaces, and then .1 up as our gateway up on the router. Router is not necessary in this specific setup since they're all on the same network, but it just kind of helps demonstrate a few extra things. Okay, so when we look at our switch, I haven't done any configuration on the switch. I've just tested a couple things prior to this video, but what we want to look at is we want to look at the CAM table, which is again also known as the MAC address table. So we'll say show MAC address table. And remember, you can use tab and question mark if you're trying to go through commands. And we can see that, only one piece of information is already kind of showing up so far. And that is the interface for my router. So what we're going to do is we're going to generate a little bit of traffic and try and figure out where things are at. So we're going to start on PC1 here, or PC0 here, rather, the .10 address. And we're going to ping over to the .20 address. And we can see that down to the bottom here, traffic is successful. So if we take a look now at our CAM table, we can see in our MAC address table, we now have two pieces of information. On our FA01, we now have the MAC address of PC0, and for FA02, it also holds the MAC address for PC1, which is the .20 address. So how is it doing that? Well, when PC0 sends the traffic out, and it's saying, hey, I want to go to PC1 over here, it's building the frame, it builds it from the datagram, then it builds it up to the TCP header, then so what protocol we're using, then it builds the IP header, which is our layer 3 header, our source and destination, IP address. So I know my source IP address is 192.168.10.10, and in this case I knew that I wanted to go to 10.20, and then it builds the layer 2 header, which is the Ethernet header, and it adds the source and destination MAC address. Well, the source MAC address is going to be PC0. The destination MAC address, however, is going to be all Fs because it doesn't know where that device actually is. So it sends out essentially a broadcast message or partially built message. and it forwards it up to the switch. The switch then looks at it and goes, well, do I know where that device actually is? No, I don't. So it forwards out a broadcast message towards all of our devices, out all devices, out all interfaces that are in an up state, that are connected to it, except for the ones that exist on its in its CAM table already. So, for instance, it would check its CAM table and goes, do I know where PC1 is at 192.168.10.20? No, I don't. The only one that I know about is this MAC address, so won't send it out there, but I'll send it to FAO2, FAO3, and wait for a response back. And the device that says, hey, that's me, and responds back, then it adds that information to its CAM table, and we see the FAO1 and FAO2 added. So let's look a little deeper into kind of the structure here. If we look at, say, Wireshark here, all I did was I just pinged a website, and how the structure of it that we're essentially seeing here is we can see really this middle section is what we typically want to look like or look at. The very top is the actual frame itself, so the full in setting. Then we have our Ethernet 2 header, so our layer 2 header. We have our Internet Protocol version 4, which is our IP header. So that's our actual layer 3, our network. And then we have our message, which in this case is the actual data, which is the ICMP. And it's just garbage information overall. So what we look at with our Ethernet header is we can see the source and destination MAC address. And so the source MAC address is my device. The destination MAC address in this case is my router, or my device that I'm trying to go out to. So the furthest point that a MAC address that I know of any given MAC address is within what's known as my broadcast domain. So the furthest point that I can see is my broadcast domain. So it's up to basically the G00 interface, and that's within my LAN. So whatever is in my LAN, this is my broadcast domain. And that's the furthest point that I can actually see, that my device can see. So that's the furthest that I will know in any given layer 2 kind of network. So we have our source and destination, and that's how our device, our switch, kind of knows how to forward traffic, is it's based off of source and destination MAC address. The switch can't read any deeper than that. It can't read into the layer 3 header, because in order to read further, it has to de-encapsulate and has to strip off the layer 2 header, which that's not something that it's supposed to do or knows how to do. So it can only read the layer 2 header. The layer 3 header in this case is my source and destination IP address. So source is my internal private IP address here, and destination is a public facing IP address going out to the internet. Now, it's private right now because I'm still within my internal network at home. So I haven't hit my router and I haven't hit NAT. So yeah, it's okay at that point. And then the public IP address is as far as I know that device is. I don't know anything past wherever I just pinged to. So on their internal network side. So hopefully that helps kind of go over a few things kind of related to kind of switching overall and how switches kind of store information. So moving on, so again, kind of mentioned the CAM table. So again, the switch uses basically two methods. It's a two-step process for learning, as I kind of went through. So it examines the source address, adds that source address to the MAC address table, and then resets the time back to 5 minutes if the source is in the table. And what that means is it will basically say, if I don't see any traffic coming from that ingress port within 5 minutes, I'll remove it from my cam table so that I don't try and forward information towards something that doesn't exist or is no longer active anymore. So it only holds information for a short duration. So this is, our cam table is stored in volatile memory, so RAM. So the next thing is, after it's the learning step, is the forwarding step, which is what I already talked about. This is how our device actually knows how to forward information, and again, that's based off the destination MAC address of where we're at. If you want a better idea of kind of what, and I'll finish up here, and then I'll kind of show another little infogram here, but if the destination MAC address is not in that table, it's going to be flooded out all interfaces except the one that was received on, in order to try and figure out where that location is. So if you want to take a closer look at kind of what our frame looks like, again, remember, it's built out from the full encapsulation phase. So we start at layer 7 and we work our way all the way back down to layer 1 when we're actually sending the message. So we structure and we build our datagram, which is the initial data that we're sending. Then we add on our header, our TCP header, for how we're going to be sending the traffic, whether it's TCP or IP. That's known as a segment. Then we add in our layer 3 header, which is our IP header, which is our source and destination IP address. And then we add in our Ethernet header, which is our source and destination MAC address. And at the tail end, it also tacks on the trailer, which is basically the closing sequence of bits to basically say, hey, this is the end of the frame. This is where we're all done. And typically this will have some sort of, say, like file checking or fragmentation checking typically built into it as well. But it depends on the protocol that we're using to send traffic. So other things that are good to kind of go over, there's two different methods for Cisco for actually sending traffic via a switch. We have store and forward, and then we have cut-through switching. Store and forward is just that. When a frame is sent to the switch, it will receive the entirety of the actual frame itself. So all of this has to actually enter into the ingress interface. Once the entire frame has been received, so once it reads that last little string of binary to tell it that it's the end of the frame, then it will move on to a forwarding decision and look at the destination MAC address and then determine how to forward the traffic out from there. Store and forward is the primary way and the preferred way that Cisco utilizes traffic on switches. Cut-through switching is our other option. With cut-through switching, the frame immediately gets forwarded as soon as the initial Ethernet header enters into the device itself. So once the initial Ethernet header enters in, it reads the destination MAC address, immediately does a forwarding decision without waiting for the rest of the frame, and then starts forwarding out an egress interface, and then just shoves the rest of what the frame is out that egress interface as well. So there's pros and cons to that for either method. With store and forward, one of the primary things there is that we have error checking, which is really nice. So it has that frame check sequence, that FCS, to check for any bad frames that might come through. That's good. It also has buffering as well, so that means that this allows the switch to have a little bit of an adjustment period to any minor differences in speeds between the ingress and egress ports. So that's another good thing. With cut-through switching, again, we have it's good in the sense that it's faster, but the problem with it is that it doesn't have any form of error checking, so it can potentially send out and propagate errors. It can also create some bandwidth issues on the switch if it sends out too many errors out towards the device. So we have to be a little bit careful with cut-through switching. Typically, most devices in our day and age can handle pretty high speeds. So you're looking at most switches in environments are at minimum 1 gig ports. I've seen 10 gig, 100 gig for a lot of those things. So at this point in time, really you don't see cut-through switching too much. Really, for the most part, it's store and forward. So another thing to kind of remember, and this is an important aspect, I kind of already briefly touched on these kind of topics in switching domains, which is we have two primary domains when we're dealing with LANs or dealing with switches. We have collision domains and we have broadcast domains. Collision domains used to be an absolute nightmare before full duplex. So when everything was half duplex, networks had to be planned out very, very carefully, because half duplex would create collision domains, meaning that if traffic went one way and traffic was trying to be forwarded the other way, a collision would occur and the traffic would get lost. That's the general gist of it. Or some traffic could get lost. So you have to be careful in those areas. Nowadays, with full duplex, collision domains are not really a thing anymore, but they are still a thing, but they're not something we have to plan around on. So a collision domain for every single network here is every single point-to-point link there is a collision domain, because they're all full duplex. So whenever you're looking at this and you're going, okay, well, which one and how many collision domains exist for? Each point direct connection to the switch is its own collision domain. So we have 4 collision domains. And then the broadcast domain is how far can a broadcast message make it within a given network, and that's our broadcast domain. So, alright, I think that about does it in terms of kind of the importance of Chapter 2. So, if you have questions, again, feel free to reach out. Hopefully that gives you a general gist of what you need to know. Yeah.